there's some good stories here, and I want you to hear them. But I also want to finish this chapter, so we'll see how far we get on the problems. Okay. Okay. So we started talking about gravitation. What we learned was the Newton's law of gravity. So if you have two objects, they attract each other. Okay. And this guy attracts him with a force, and this guy attracts him with an equal and opposite force. So the magnitude of the forces are equal. Okay? The directions are opposite, of course. And the magnitude of this force is given by this equation that Newton came up with. Okay. There's a universal gravitational constant. It's the magnitude of the force is this constant times the product of the masses divided by the distance squared. Okay. Now you saw that this law is good enough as long as you're dealing with weak fields, meaning the sun attracting the earth attracting the moon, and so on. But if you start playing with black holes that are close by, then this guy is not good enough. Okay. So you saw that that law is good for weak fields. Okay. And again, if stuff is moving fast, then you need to add special relativity in there. Okay, so if you're dealing with strong fields and fast-moving objects, then you really have to do this. This is a much more complicated theory, the general theory of relativity, which Mr. Einstein came up with. Okay. So this is what we're dealing with. And again, if you want to marry the ultimate theory, the correct theory that works in all situations is the quantum theory of gravity. Okay? This approximation is good enough as long as you're talking about black holes going around each other and so on. Okay? This approximation is good if you're talking about the sun and the planets and so on. Okay? And this will reduce to this in where there's no gravity and stuff moving fast. Okay? Okay, this is the correct theory, and these are various approximations in various situations. Okay? Do you guys understand that? All right. All right, so this is the guy we're dealing with. And that guy is this. Okay, so this formula gives you the magnitude of the force between the two objects. You guys understand? All right. So we saw all of this last time. Okay, so the magnitude of that force, okay. So here's Newton's law of gravity. That's the product of the masses, and that's the distance between the two objects. Here's this universal gravitational constant. Now, Newton came up with this in 1687. But when he came up with that, we didn't know the value of this guy. And this guy wasn't measured till 115 years later. Okay, and measuring this constant was a crucial thing. And Mr. Cavendish measured this. Okay, and this was his experiment. Okay, soon as you measured that, we could get the mass of astronomical objects. So, for instance, the mass of the Earth could be gotten because we knew the radius of the Earth. This is the acceleration due to gravity on the surface of the Earth. And once you measure this, now you know the mass of the Earth. Okay, so this is when we learned the mass of the Earth, 1800. Okay? And that evening, we also knew the mass of the sun and all that kind of stuff. Okay? You guys understand? Yeah. All right. What is the acceleration due to gravity? Okay. And which way is it? Is the acceleration due to gravity a scalar or a vector? It's a vector. Which way is it pointing? Downward. I'm sorry? To the center of the Earth. That's the more precise statement. Okay. And so it's the magnitude is 9.8 meters per second square near the surface of the Earth. If you go high up, it decreases. Okay. So that acceleration vector is drawn here. See, all those vectors are pointing toward the center of the Earth. Okay. And the magnitude is decreasing as you go high up. Okay. So this is a vector field. This is the gravitational field. Okay. And this is just plotting G as a function of X, Y, and Z. Okay. And it happens that G is only a function of R. Okay. And that's equal to, and there's the function. This is a unit vector pointing radially outwards, and G is pointing in the opposite direction. All G is pointing in this direction. Okay. All right. So, for instance, what this table says is, okay, the radius of the Earth is 6,400 kilometers. So if you're 6,000 kilometers above the surface of the Earth, see the magnitude decreases to 2.6 meters per second square. On the surface, it's 9.8 meters per second square. So what this is saying is, there's the length on the surface, that's the length of that vector is 9.8 meters per second square. And 6,000 kilometers up, the length of that vector is 2.6 meters per second square. Did you guys understand that? That's what that's showing you. We saw that, this was interesting, we saw that yep.
By slide, what was the R with that hat on it? The variation.
Okay, so have you done polar coordinates yet in your calculus classes? Spherical polar coordinates? Okay. All right, so these are the Cartesian coordinates. What is I? I is a unit vector along the x-axis. J is a unit vector along the, okay? And now I was being lazy. People draw with hats, okay? So, these are the Cartesian coordinates, but for a point, okay, and in math, they do it slightly different. So this angle is theta. And in physics, we call this angle phi. Okay, so the coordinates of that point can be given in the Cartesian coordinates or r, theta, phi. These are called spherical polar coordinates. Okay. And so and what is r? R is this distance from the origin to that point. Theta is the angle this vector makes with the z-axis. And phi is the angle the shadow of that on the xy plane makes with this axis. Okay. So just like you had I, j, k unit vectors, we have r hat, okay, and theta hat, and phi hat, which goes there, phi hat. Okay. So you need three unit vectors that are perpendicular to each other. So there's the r hat. All right. So why do we have different coordinate systems? They're different languages. So for instance, if you're dealing with trying to solve problems like this is this gravitational field, this kind of problem it's good to solve in spherical polar coordinates. Let me write that in Cartesian coordinates. okay, minus gm x square plus y square plus z square, okay. R hat will have to, now R hat, oh man, this will have to be sine theta cosine phi I plus sine theta sine phi j plus cosine theta k. Now solve this problem. Okay, why would you do it in that coordinates when it's so simple in this coordinate system? Okay, so that's why we have different coordinate system. Based on the symmetry, you choose the language in which you solve the problem. Okay, did you guys understand that? Okay. Yeah. All right. I have this. All right, so here was an interesting thing. So you learned that the only place a building is vertical, meaning perpendicular to the ground, is on the equator and at the poles. If you build a building anywhere else in the northern hemisphere, the building is actually leaning towards the North Pole. Okay? In the southern hemisphere, it's leaning towards the South Pole. And again, like I said, for the tallest building, this is a few feet at the top, meaning this gap is a few feet. Okay? All right, you saw that the gravitational potential energy close to the surface of the Earth. So if this is the surface of the Earth, this object has potential energy, and the potential energy of this object is given by its mass times g times its y coordinate. Okay? When is this expression good? I'm sorry? I'm sorry?
Close to the surface.
Close to the surface of the Earth. It's good as long as g doesn't change. Okay? Which is, and close to the surface of the Earth, you can ignore all changes. Let's say even if you jump 40 kilometers high, you can still use this guy. But if you jump 4,000 kilometers, now you can't use that. Okay? All right, so you want to use this when you can get away with it. But if you are jumping 4,000 kilometers, now you need a better expression, and this is the more accurate expression. The potential energy between two objects is minus gmm times the product of their masses divided by the distance. Okay? So in this definition, the potential energy is 0 for r equal to infinity. Okay? So if you wanted to calculate the potential energy for a solar system, for instance, multiple objects, you calculate the potential energy of this pair plus this pair plus this pair. There's the potential energy. What does this energy represent? Let's say, so if these guys were at rest, that would not be possible, but anyway, let's say these guys were at rest and they're attracting each other, and you want to take them away to infinity. This is how much energy you would have to put. Okay? So if this was a minus 1,000 joules, you take a minus 1,000 joules and they would go all go to infinity. Okay? We learned the idea of escape velocity. What is escape velocity, my friends? What's that?
Be able to get away from that gravitational.
Right, so you throw an object, and if it goes all the way to infinity, then it has escaped your gravitational field. Okay? And so from this object, from this position, from this height, from this distance from the center, that's the escape velocity. Okay? And then we learned a very important thing. Okay? We learned that nothing can go faster than the speed of light. So you can take any object and squeeze it to a radius such that this escape velocity became the speed of light. What you have done is you've turned the object into a black hole. Okay, all right. So here are escape velocities for various objects. I'd like for you to remember this. The escape velocity from the Earth is 11.2 kilometers per second. So the speed of all satellites that are orbiting the Earth is less than that. Otherwise, they would escape. Okay, so the speed of the space shuttle is, what is the speed of the International Space Station? You guys remember? Huh? 18,000 miles an hour, 8 kilometers a second. Okay. Roughly about 18,000 miles per hour. Okay. All right. So here was as long as the force between two objects is given by m1, m2 divided by r square, as long as this force law is correct, the only orbits that you can have, so if this was very massive, the orbits this guy could have around this guy, so if this was the sun, the orbit of this guy, of Earth around the sun, has to be one of two things, one of four things. It can be circles, ellipses, parabolas, or hyperbolas. Okay?
Can you keep that for me? I'm sorry.
Mm-hmm. Okay, I'm going to tell you about the detection of gravitational waves. I can't wait to tell you about it. In my opinion, it's the greatest experiment done ever. Okay? Well, okay, one of the greatest. Mine is a biased opinion. All right. All right, so as long as this is the force law between the two objects, and let's say this is a massive object, this is a light object, the orbit of this guy can be a circle or an ellipse. This is if the total energy, is kinetic energy plus potential energy. Okay? So the total energy of this guy is, if it's less than 0, then it's a bound orbit. Bound meaning it just goes around it. Okay, so all planets go in elliptical orbits. And if this law is correct, they'll go in that ellipse for how long? For how long? If there's no friction, forever. Okay? And this is, you have a parabolic orbit for 0 total energy, meaning it'll come from infinity and go back to infinity. Hyperbolic orbits where energy is greater than 0, it comes from infinity, goes to infinity, and it still has kinetic energy left. Okay, so Kepler's first law says planets go in elliptical orbit. Ellipses have two foci. There's the center of the ellipse, and the sun is at one of the foci. Okay. So you saw all of that. So let's see if you guys remember this. This is Mercury's orbit, and I'm not going to go into the details. Okay, so here's Mercury's orbit. The ellipse is precessing. So what does that mean? So again, let me restate this. If this guy was an absolutely precise law, then the orbit would be an ellipse and it would go on in that orbit forever. But look at this, Mercury's orbit is not elliptical. That ellipse is precessing. So that right away tells you that, okay, even though Newton was pretty darn smart, this is an approximation. Okay? You had to see its flaws, you had to get close to the sun, you had to get to a stronger gravitational field. Okay? To see its flaws. You don't see its flaws if you're looking at moon's orbit around the Earth, you can't see the flaws. Okay? You had to get to a stronger field. You guys understand what I'm saying? Okay. So, and this measurement is absolutely amazing. But anyway, we got to talk about more amazing things, so we'll give that one a miss. All right. So, Mercury's orbit tells you that this guy is an approximation. Okay? And this was a better theory that explained Mercury's orbit. Okay? But look at this, 1687, 1916, that's 225 years. It took us 225 years to advance, take this step to that step. And this guy is still not the final word. This guy is the final word. We don't have it yet. Okay? All right. I hope I'm not, I hope you guys are able to follow this. Okay. Kepler's second law says that a planet going around the sun sweeps out equal areas in equal time intervals. So if this was the area swept out by the planet in 1 month, this is another month, this is another month. Okay? So the closer you are to the sun, the faster you're going. The further out you are, you're going slower. Okay? This is Kepler's third law that says, so let's assume a spherical orbit. If this little mass is going around this big mass, its period square divided by radius cubed depends only on the central mass. So what this Kepler's third law is saying is, oops, so you can have a million objects going around this object. For all of these guys, you take their periods divided by the radius cube. That's related to the central mass. So for instance, we got 500,000 objects going around the Earth. You can take the period of each of those objects, divide by radius cube for those objects. You'll all get the same number, and which will be related to the mass of the Earth. Okay. So for instance, this space shuttle or the International Space Station goes around the Earth. So its radius is essentially the radius of the Earth. It goes around the Earth in 90 minutes. So you can put that 90 minutes, put the radius of the Earth, and you can calculate the mass of the Earth. Okay. So if you wanted to calculate the mass of the sun, you can put the numbers for the Earth. For the Earth, that would be 1 year, and the radius is about 92 million miles. Okay? You put those numbers and you can get the mass of the sun. Go try that at home. The mass of the sun, this is the notation, is 2 times 10 to the 30 kgs. Okay? Try and do that calculation. And of course, you have to put this in seconds, this in meters, and so on. Okay? What this formula is giving you is, it's giving you the speed of a satellite going around the Earth in a circular orbit. And you see, as r increases, the orbital velocity decreases. All right, so we talked about all of this last time. So these are the geostationary satellites. These are low Earth orbit satellites. There's a lot of stuff out there. And we are putting in more and more stuff. So Elon is putting out all these satellites in orbit so you can provide free internet. I mean, not free internet. Oh man.
Nice.
Have you guys looked into getting Starlink? Does anybody, have you priced it? $120 a month. Yeah. All right, so that's where we were. Okay, I'm going to, any questions so far? Okay. I'll let you guys read. If I'm skipping it, that means you're reading it on your own. Okay. All right, so we want to understand tides. Okay. Mr. Newton explained tides. Okay. So here's the deal. Okay, so the tides is, you see here's a bulge. The ocean has bulge. Okay, this you can understand. Here's the moon. This stuff is closer to the moon, and so it got pulled, and that bulge happened. Why is the ocean bulging over here? That's further away, right? Okay, so Mr. Newton explained this, okay, by the way. So before we explain this, okay, so the tidal force can be viewed as a difference in force between as the difference between the forces at the center of the Earth and that at any other location. Okay, we'll come to that. The change in sea level caused by these tidal forces is measured from the baseline sea level. The Earth bulges many kilometers at the equator due to its rotation. Okay, so what that statement is saying is, if the Earth didn't rotate, that would be the shape of the Earth. But because it's rotating, it's already bulging several kilometers at the equator. Okay, this is several kilometers. So this tidal bulge is a few meters above that bulge. Okay, so that's the baseline. Okay, so that's what we're talking about. All right. So Earth bulges this defines the baseline sea level, and we consider only the much smaller tidal bulge measured from the baseline sea level. All right, so now okay, so let me state this following. If the Earth were a point object, you wouldn't have tides. Well, I mean, so you have to have an extended object to have tides. Okay? So now let's do the following. Okay, so here's the moon, here's the Earth, and here's the ocean. Okay, we are trying to explain this bulge. Okay, this is sort of more intuitive to understand. Okay. Now, what is the force between? What is the Newton's law of gravity? Okay, so the force depends on how far you are. Okay, so this is the moon. The force of the moon on 1 pound of the stuff, or 1 kg of the stuff, let's say, is 100 units. Okay. What will be the force of the moon on 1 kg of stuff here? What's happening? Delayed reaction?
I think it's going back. We already did all of that.
Is this messing up the recording?
Have you ever seen? No.
I hit rewind somehow in the recording.
You might have stopped it and hit rewind.
Well, on my iPad, it's, okay. Well, I hope it's recording properly. Okay. So here's the moon. It attracts this 1 kg of object at 100 units. What would be the force on this guy? On 1 kg of stuff here. This guy is closer, so it'll be greater than 100 units. So let's say it's 102 units. You guys understanding this? What would be the force on this guy? I'm sorry?
The same.
Well, this guy is further away, so that would be less than 100 units, 98 units, let's say. I'm making up numbers, okay? You guys understand? On this guy to roughly 100 units, except like in this direction, 100 units in this direction, toward the moon. So now let's do the following. Let's make rescalar units. Let's call 100 units 0. Okay, now let's redraw the forces. This is 0. This guy is 2 units in this direction. What is this guy? I'm sorry? Right, 2 units in that direction. And there's a component of the force in this direction, there's a component of the force in that direction. And that's what's shaping that. So that's what's happening. So essentially you can think of this as, okay, so this, think of that as being at rest, and the force on the earth was greater and it was being pulled away, and so that's what left the bulge there. Okay? So that's what, so there's the 2 units, negative 2 units, and so on. Okay? So that's, like I said, Mr. Newton explained the tides. Okay, so if you think about it, what matters is, for a tide, if an object is attracting you, what matters is what is the differential force. It's pulling you harder in this direction, and this is being pulled away, which is effectively acts like this guy is being pulled in that direction. Okay, so what matters is the tide, the height of the tide will depend on this difference in force. Okay, so for us it turns out that, well, the sun is a stronger body, except that it's so far away that the differential pull of the sun is smaller than the differential pull of the moon. So the moons cause most of our tides. Okay, so here's what this gives you: tidal force per unit mass. What that tells you is the following. What is the difference in force per unit mass across the diameter of the Earth? Okay, per kg. And for the sun, it's 5 times 10 to the minus 7, and for the moon, this number is 11 times 10 to the minus 7. Okay, so this force minus this force for the moon is 10 minus 11, and for the sun is 5. So the tidal force for the moon on Earth is twice as much. Yeah. So that's what those numbers tell you. All right, so on Earth, you'll have the highest tides when the sun, Earth, moon, and the sun line up. Okay, so this tide and this tide will be equal, and they're highest. When the moon and the sun are perpendicular to each other, their tidal forces are working against each other. So this tide will be about, this is 150%, this is 50%. Okay. All right, so this kind of stuff is important in astrophysics. So let's say here's a massive object, and if this star expands, this object can rip stuff off if this stuff gets closer to it. Okay? So the tidal forces can rip material off a nearby object. Okay. This happens to be a black hole, and this expanding star is losing material to the black hole where an accretion disk is formed. Okay. So if this stuff fell directly, it would fall directly into the black hole, but if it's at a glancing angle, it'll rotate like that, and this stuff can be at millions of degrees Kelvin. Okay, very hot. Okay, so we'll talk about general relativity for 3 seconds, okay? um, so this is Newton's law. Okay. General relativity is an upgraded version of that. Okay. So this was good for weak fields. This is good for stronger fields. Okay. And this guy and Einstein doesn't care if objects are moving close to the speed of light. And we will show you a situation where objects are moving close to the speed of light. Okay. All right, so what does Mr. Einstein say? Okay. So Einstein says the following. If there is no stuff in the universe, then space-time is flat. Okay, now if you go to a store and buy a star and put it there, what the star does is it curves space-time. Did you guys understand that? So if there was no stuff, space-time would be flat, but if you go buy a stuff and now it curves space-time. So this could be the sun, and space-time is curved around the sun. All right. If there was no stuff in the universe, space-time is flat, you go buy a marble and you shoot a marble, how will the marble move? So think of you shooting a marble on this table. How will the marble move? In a straight line, right? All right, so when there are no forces acting on an object, a marble moves in a straight line. Okay, Einstein says you go buy an earth or a marble, shoot it, and in curved space-time, this orbit, that's a straight line. It's called a geodesic. And that's Einstein's general theory of relativity. Okay, so I'm going to state it again. Matter curves space-time. Curved space-time tells other small bits of matter how to move. And how are they moving? They're moving in straight lines in that curved space-time. Okay? So here's a very famous state. Matter tells space-time how to curve, and curved space-time tells other bits of matter how to move. Okay, so I'll give you a little puzzle to think about. Okay. Do you guys know how long it takes light to reach Earth from the sun?
8 minutes?
8 minutes? Okay, all right. So here's the sun, and you guys know that the Earth is going around the sun. Yeah, let's think of the following. Okay. Let's say you go home, flip a switch, and make the sun vanish. what will happen? You guys understand the question? You,
Will just continue on its tangential.
very good. Very good. You make the sun vanish, it'll just go on a tangent. You can think of the following: tie a rock to a rope and whirl it around. Soon as you cut the rope, it'll go. The next question is the following. So here was the sun. I made it vanish. It goes on a tangential path. When? When does it know that you made the sun vanish?
After 8 minutes?
There you go. Okay, between you two, you got it. Okay, so a question, Newton couldn't answer this question. It took Einstein's theory to answer that question. Okay, and here's what's happening. Okay, so when you make the sun vanish, well, this space-time was curved. It has to flatten, and it flattens at the speed of light. So the space-time was curved near where the Earth is. The Earth won't go in a straight line until the space-time gets flattened there. And that happens at the speed of light. Okay? So Mr. Einstein was able to answer that kind of stuff. Okay, I'm just making up a little example. Okay, so Einstein came up with this theory in 1916. So here, matter, curved space-time, and other small objects, they're going on geodesics, and these are straight lines in curved space-time. Okay. What do we mean by that? I'm going to just write a mathematical formula, just a little. Okay, so okay, when we say this is flat space. Okay, so here's x1, y1, z1, x2, y2, z2. Okay, how do we say what is a straight line? Well, that's the shortest distance between the 2 points. And that distance is delta x square plus delta y square plus delta z square. Okay, so that's how we calculate the distance between them. Okay, and the straight line corresponds to where the distance is the shortest. Okay. In space-time, here's how you measure the distance. Okay, the formula is very similar, except that here's how you measure the distance in curved space-time. And I'm writing a very simple formula. Okay. Okay. So just this formula got altered like that. That's all. Okay. And along this path, this distance is the shortest. And so that's a straight line. Okay, so that's how you measure distances. Okay, and that's that guy in Einstein's equation. Okay, and these guys are related to that. So this is what Einstein is famous for. This is related to distribution of matter and energy, and this stuff is related to the curvature of the space. So Einstein's equation is telling this distribution of matter is telling space-time how to curve. Okay. All right. I urge you guys to go watch that video. Okay. Again, this is we talked about black holes. So let's say here's a star. Here's a star of mass m, and that's the escape velocity from here. Okay. Now, if you start squeezing this star, if you squeeze it inside this radius, this is called the Schwarzschild radius. If you squeeze this object star inside the Schwarzschild radius, from this point the escape velocity becomes equal to the speed of light. Okay. And in fact, it turns out if you squeeze the star beyond this point, it just keeps collapsing. And Einstein says it collapses all to a single point, but we know that's not right. You know, we don't have an answer to that. So for instance, the sun has a radius of 700,000 kilometers, and for the sun, this radius is about 3 kilometers. So if you took the sun and squeezed it by a factor of 200,000, you can turn it into a black hole. Yeah. I know you guys are getting tired, so but I want to finish the lecture. Here's a black hole. There's stuff falling into the black hole. There's the accretion disk, and that is very hot stuff, and it emits X-rays, and these X-rays are related to the property of the black hole. Okay? And you see there's jets of stuff that comes out along the axis of rotation. Okay.
Is that gas escaping or no?
I'm sorry?
Is that gas escaping?
Yeah, escaping
So
along the magnetic field.
traveling
So,
at the speed of light?
I'm sorry?
Is it traveling at the speed of light?
All right, so good question. So from the Schwarzschild radius, the escape velocity is the speed of light. But that gas is escaping from here. It doesn't have to, but it's going close to the speed of light anyway. All right, so these are Hubble Space Telescope pictures. So there's the black hole, there's the jets. Yep. You guys know that we live in the Milky Way galaxy, which is a spiral galaxy. And at the center of most galaxies, there are massive black holes. Okay, so you know Kepler's third law? So here's a little object going around this massive object. So this could be the Earth going around the sun. This could be a satellite going around the Earth, and so on. But you saw that t square, the period square divided by radius cubed, equal to 4 pi square g mass of this object, of the central object. Okay, so if you can measure the period of an object and measure the radius of the object, you can calculate the mass of this central object. Did you guys understand that? All right. So here's okay. So at the center of this galaxy is a massive black hole, but you can't see it. So how do we know there's a massive black hole? Well, these are stars going around that massive black hole, and they're going crazy fast. A star is traveling close to the speed of light. Anyway, they can measure these periods and they can measure these radius and calculate the mass of this central black hole. This is not an easy measurement, but they do it. Okay? So it's estimated that a black hole of about 4 million solar masses resides at the center of our galaxies. There are other galaxies where the masses are billion solar masses. Okay? I see that people are getting tired, so okay. Okay, let's. Okay, gravitational fields will bend light as well. Okay, all stuff travels in straight line. In curved space-time, this is how a straight line looks. So if this was a star, light coming from there, that's a straight line in curved space-time. Okay, so this light got to you, but biologically what you hardwired for you, this is a straight line. So there was the star, its light got bent, and what you see is the star there. So how could we verify this bending? Are there stars out there in the sky right now? Why don't you see them? This light is swamping it. Okay? So, but how are we going to verify this guy? The sun is there. Wait for a total solar eclipse. Get the moon to block that light. And then there was the star. There's the actual position of the star. And it appears in the sky over there. Well, how do we know that's the position of the star? Okay, wait for 6 months when the sun is over here. Get a picture of the same part of the sky, and well, you've already gotten that picture and you compare it to that. Okay, this star will have moved relative to further away stars. Okay, so this bending of starlight was verified in 1919, and that was one of the first confirmations of experimental confirmations of Einstein's theory. So here's now, these are modern pictures. Quasars are very bright objects. These are supposedly massive black holes eating up stuff. So they're some of the brightest objects in the universe, and so you can see them from far away. And so here's the gravitational lensing. So light from here bends around this massive galaxy, comes here, and this one object, you're seeing two images. So here's an actual picture, and there's the intervening galaxy. There's that galaxy. And the claim is that these are the same objects. Well, how do we know they're the same object and not two different objects? You guys understand what I'm saying? Somebody gave you a picture, and how do we know that they're the same object? Looks two different objects to me. So here's how you tell. You separate the colors. Colors are, different colors have different wavelengths, so you separate the colors and measure the intensity. Okay, so this is the spectral intensity, and the spectral curve is identical for both the objects. So they're the same object. Okay. All right, dark matter. So I want to get to my story, so I'm going to skip this. But so the universe today is roughly 68%, or we'll keep it simple, 70% dark energy, 25% dark matter, and 5% normal matter. Okay. I could do a better diagram. Oops. 70% dark energy, so 5% normal matter. Okay. This curve, which was measured in the 40s, is one of the first evidence of dark matter. Okay, so I'll quickly go over the curve. Okay, so here's a star. If it's going around this galaxy, all this matter inside is affecting its orbital motion. Okay, so the centripetal force, that's the star, mass of the star, mv squared by r, is this m is the mass of all this guy. Okay, that's that m. And so you solve for v. V is 1 over square root of root r. Okay, so if you're past this, do you see any more stars past this point? You don't see any more stars past this point. So once you're past this point, the speed of the orbital motion of the star should decrease as 1 over square root of r. So you're going further, but you see the orbital speed is not decreasing. That tells you there must be more matter there, that this guy is not done yet. That was evidence of dark matter. Okay? All right, so all this blue stuff is dark matter. I mean, these are all same images and so on. So these are computer simulated, this dark matter. We don't know what dark matter is yet. Okay, and you've heard some seminars on these. Yeah. Okay, again, this is the greatest experiment, and I'm going to spend 30 seconds on it. I'll tell you about it. I know you guys are tired, but I hope you want to hear about it, and I'm going to tell you about it even if you don't want to hear about it. Ilyana is falling asleep. No? All right. So here's the deal. All right. If you take a proton and you jiggle it, so if you make a proton accelerate, it will send out electromagnetic waves. You take a mass, let's say 1 pound mass, you jiggle it, it'll send out gravitational waves. Yeah. Now, the electromagnetic force is very strong. The gravitational force is very weak. Okay? You take a proton, there's a chance you can detect this guy. You take a 1 pound mass, so you can jump up and down, and you emit gravitational waves. Except that these are so weak, there's no way in hell you're going to detect them. You can take the Earth and jiggle it, and it'll send out gravitational waves. You can't detect those either. That's not massive enough. You want to detect gravitational waves, you'd have to grab hold of a massive black hole and jiggle it. And maybe you might detect these gravitational waves. How do you jiggle the Earth? So what you have to do is you have to make a mass accelerate for it to emit gravitational waves. How do you jiggle the Earth? You got the sun doing it for you. Here's the sun, and the Earth is going around. Remember, that's just oscillating. So now we have a way to jiggle objects. You want to jiggle a black hole, just recruit another massive black hole. Okay, the universe is full of binary stars, okay? So these guys orbiting around each other, they will emit gravitational waves. All right. So now we know how to produce gravitational waves. So every time you jump up and down, you're emitting gravitational waves. So there's gravitational waves being emitted all the time. Every planet going around every moon going around a planet is emitting gravitational waves. Every mass accelerating is emitting gravitational waves. Except that those waves are so weak that there's no way you're going to detect them. You have to have a very massive object accelerate, and then you can potentially detect those gravitational waves. Okay. All right, so we detected this one event in 2015. And I'm going to tell you the stuff. It won't register. You'll go home, read the slides again, think about it, and maybe it'll sink in. It is absolutely amazing. All right, so what happens if a gravitational wave goes by? Okay. So So let's say here was a circle. Okay. When a gravitational wave goes by, this circle, right now it's like that. It will stretch like this. Okay, so here's the one quarter of the cycle, it'll stretch like that, go back to this shape, and then stretch like this. Okay? So when the gravitational wave goes by, this space stretched like that, then went back like this, and then stretches like that. Okay? And then it, as long as the wave is going back, it keeps, that pattern keeps repeating. So if you want to detect this gravitational wave, you want to measure this change in shape. Okay, so in 2015, we measured this gravitational wave that went by. We measured roughly, it passed, okay, so this gravitational wave was passing for a long time. We measured about 200 milliseconds worth of it. So somebody wasn't, it's all automated. Well, how much did the distance change? Okay, if this diameter was 1 meter, this thing changed to 1 meter plus 10 to the minus 21 meters. Okay, let me put it another way. If this was the Earth-Sun distance, how much is the Earth-Sun distance? 92 million miles. This changed by the width of an atom. All right. Okay, so let me state this again. This gravitational wave went by. The Earth-Sun distance changed by the width of an atom for about 200 milliseconds, and we measured that. And we believe we measured that. No, we are very confident we measured that.
It's a lot of faith.
Yeah. So how do you measure that? Do you guys understand this? Now to put it in perspective, okay, so 1 meter, here's 1 meter. This changed by 10 to the minus 21 meters. So let me put this in perspective. The size of an atom is 10 to the minus 10 meters. The size of the nucleus is 10 to the minus 15 meters. The size of the proton is 10 to the minus 18 meters. This is a width 1,000 times smaller than the, okay? All right, you guys understand the magnitude of the problem? All right, so now you see why it's beautiful, okay? All right, so here's the black holes being jiggled, okay? I'll come to these numbers in a second. Let me tell you how to measure that distance, okay? Okay, so here's the instrument. Here's the LIGO detector, and we've had talks of the LIGO detectors here. So if you guys are around, well, anyway, okay, so here's the idea. This is the detector in Louisiana, okay. What you do is you send a light beam, like a laser source here. This is a partially reflecting mirror and partially transmitting mirror. So here is a beam. It splits the beam into two portions, okay. So this beam travels over there, reflects, and then comes back. This beam goes over there, reflects, and comes back. And these two beams meet, and the way it's set up is one beam reflected back comes like this, the other beam comes like that. So when you, at the detector, this beam is canceling that exactly. You guys understand? All right, if a gravitational wave passes by, you see this length stretched. Now this beam is traveling a larger distance, so it doesn't, when it comes back, it doesn't quite match. And it's not canceling anymore. Okay? So when this stretches, there's light. And similarly, when this stretches, there's light. So if there's not exact cancellation, then maybe a gravitational wave passed by. Or maybe a truck drove by. You guys understand? Or some guy, the cross-country team was running and that induced light.
Is it happening constantly, or
I'm sorry?
is this happening constantly, or you just had to figure out and just wait for one?
Well, so if you're jumping up and down, you're changing this thing, but you're changing that thing by so little that that won't be detected. Okay? Even this massive black hole, I'll come to those numbers in a second, okay? It's just mind-blowing. But did you guys understand? So how do you detect it? All right, now how do we confirm this was actually a black hole? That this was a signal from the black hole. So, well, of course, I mean, this is serious business. So there's the LIGO detector in Louisiana. That's several $1 billion. So to make sure that that's actually a signal, you spend a few more $1 billion and build another detector over there. If these two guys got the exact same signal, it wasn't a truck, it wasn't a cross-country team, it was a gravitational wave. Okay, and now we're going to build detectors all over the world, okay, to do that. Okay, now let's do some of the numbers. I'll put it in perspective. Do you guys know how old our sun is? How old is our sun? 5 billion years old. Okay. How much more life does our sun have? Another 5 billion years. Okay. So our sun has a lifespan of 10 billion years, and then it'll die and whatever, it'll become a brown dwarf. Okay. Okay, so if the sun is producing, there's nuclear fusion going on at the center of the sun, and so it's losing mass and turning that into energy. Okay, so if the sun was 100 pounds to begin with 5 billion years ago, in 5 billion years, I'm just making up these numbers, it'll be roughly 98 pounds. The sun will lose about 2% of its mass over a span of 10 billion years. Okay? So now I'll give you the numbers. So these binary black holes were revolving around each other for millions of years. They were losing energy. So they're revolving around each other. They were losing energy millions of years. And as they lose energy, they're getting closer. Okay? And the orbital radius is getting smaller. Okay? And then they get closer and closer, and then they merge. We saw the last 200 milliseconds of it. Okay? So we couldn't detect any of those waves that were being sent for millions of years. Okay. We just detected the last 200 milliseconds, and that's the signal. See, there's 0.25 seconds, 0.45 seconds, 200 milliseconds. Okay, now we'll come to the numbers. Okay, so this one black hole was 36 solar masses, and this one was 29 solar masses. So that's a total of 65 solar masses. Okay. So, and they're radiating energy, and they're losing mass, and when they merged, they became a 62 solar mass object. And most of the energy was lost in the very last few milliseconds. They lost 3 solar masses, let's say in 200 milliseconds. Let that sink in. How much mass is the sun losing? I'm sorry? This much mass the sun is losing. Over what time? 10 billion years. In this merger, 3 solar masses were lost in less than a second. So the amount of energy radiated for those 100 milliseconds was 100 times greater than the energy emitted by all the stars in the universe. Let me restate that. The energy radiated in the 100 milliseconds, in the last 100 milliseconds, was 100 times greater than the energy emitted by all the stars in the universe in the 100 milliseconds. And we barely detected it. Okay. All right. So when you go home and read about it, so the black holes were going around at about 100 times a second at relativistic speed, 0.6 the speed of light. These massive black holes are going at 0.6 the speed of light. Yeah. Peak strain, so that was the most intense gravitational waves, lasted about 50 milliseconds. Okay. All right. That's enough of that.